Hi, welcome to this third part of the tutorial series on inertial focusing of particles using COMSOL multiphysics. In the previous video, I created the geometry in CATiA. In this part, I'm going to show you how I can import the geometry into COMSOL and start the simulation. So I'll open up COMSOL and click on the blank model option. Once I do, the simulation environment opens up and I can start the simulation by adding my geometry into COMSOL. So I'll just right click on this untitled MPH file and use add component and 3D component so I can locate the file that I saved into my computer earlier on, the IGS file if you remember from the second video. So I right click on the geometry and hit import, and here in the settings panel I click on the browse option and browse into wherever I located my spiral IGS file here in my desktop. I hit open and then import the file into COMSOL. It should take a couple of seconds until I see the geometry in this window here in the upper right. Once the geometry is imported into COMSOL, I can actually add in the material that I want, which in our case is liquid water. So I just go ahead and right click on the material here. You can of course use this panel up in the upper part of the window as well. I right click on the material and add material from library. I can be able to use liquid water from the liquids and gases part, and because I've recently used water, I can go ahead into recent materials and choose liquid water. Now it's loading my materials. As you can see, I can choose water, liquid, and double clicking on it will add the liquid water into my materials. After adding the geometry and material, what I want to do is to add in the first physics. Now, remember, we want to use two physics for this simulation. The first one is the laminar flow, and the second one would be the particle tracing for fluid flow. The laminar flow will be the first thing that we'll add into our geometry. So I'll just go ahead in the upper panel here where I can choose my physics. I click on it, and in this panel I've recently used the laminar flow, so I'll just double click on it to add it to the model builder. It takes a couple of seconds, and now as you can see in my model builder, the laminar flow physics is added. I will go ahead in the laminar flow options itself, and I really shouldn't change any of these presets except for the discretization method. The discretization of the fluid needs to be greater than P1 plus P1. The reason behind this is that this needs to account for the actual shear gradient force that acts on particles. So if I leave it to be at P1 plus P1, the shear gradient lift wouldn't take into account, and only the wall-induced lift forces, which we'll add in later, will act on particles. So you have to make sure that you choose something greater than this P1 plus P1. I'll choose P2 plus P2 for this fairly simple model. Once I do, I go to the fluid properties. Nothing needs to be changed here. In the initial values, nothing needs to be changed. And in the wall conditions, we make sure that it's set to no slip as its default option, and we are not going to change that as well. The next thing that we have to add is the inlet velocities. Now, we have two inlets, as you can see, this inner inlet and the outer inlet. From the information that's given to us in the actual paper, we can calculate the Reynolds and convert it to the velocity of the main channel using a simple calculation, and then determine what velocity each of the inlets should have. Now I've calculated it already, and I know that the inner inlet, which is this bigger inlet here, needs to have a velocity of 0.45 meters per second, and this outer inlet should have a velocity of 0.1. So I'll just right click on the laminar flow physics and choose inlet, and now this gives me that I should select the boundary that I want the inlet to be. I select this inner inlet here and type in for the normal inflow velocity the amount that I should be, which is 0.45 meters per second. I right click on the laminar flow again and add in another inlet boundary layer here This time the outer inlet should be 0.1 meters per second. So we've added two boundary layers, two velocity boundary layers. Now once these two velocity boundary layers are added, I can go ahead and determine the outer boundary layer, which is a zero pressure. I right click on the laminar flow and choose outlet, and here choose the two outlets that I got and leave the default, which is a zero pressure outlet boundary layer. Once you're done, you can continue and calculate the velocity field using a stationary study. But before that, we have to use a mesh. And for this model, it's okay to use the coarser mesh and a physics controlled mesh, which is a laminar flow. And once you click build all, COMSOL will automatically mesh the geometry for you. And since I've used this mesh for the model and it worked, it's really a good option to use the built-in meshing option of the COMSOL. It gives you a warning which tells you that some of the faces are smaller than the indicated minimum, but it's not really that much of an important warning. So I'll just leave the mesh to be this built-in coarser mesh, and up until now I've added everything about the laminar flow. We are free now to use the study to see the actual velocity field. So I'll go up in the panel here and I choose Add Study and Stationary Study, because the velocity is going to start from the inlets and reach stationary final value. So we can use the stationary study for the velocity field. All right, in the option bar for the velocity for the stationary study, nothing needs to be changed at all. So we'll leave everything to be the default, and right-clicking on the study 1, renaming it will give us a better understanding of what we're doing later on. So I'll type in VF for velocity field for the first study, and I hit OK and click on Compute. Now it should take a couple of minutes for COMSOL to calculate the velocity field, and once it's done, we'll continue to see how the particle tracing for fluid flow physics works in COMSOL. Alright, now after a couple of minutes, the velocity field is calculated by COMSOL. I can continue adding the particle tracing for fluid flow physics to see how the particles will interact with their environment, the walls, the shear gradient lift force, and obviously the Dean drag force. Now the Dean drag force doesn't have to be added in the particle tracing for fluid flow as a separate force, because it's actually somehow embedded in the velocity field that's actually calculated. So we are going to add the particle tracing for fluid flow physics right now. I click on the Add Physics and use particle tracing for fluid flow, which is something that I recently used, so it will be up here. If it's not a recently used physics for you, you can go under the fluid flow, and under particle tracing you can find the particle tracing for fluid flow physics, and clicking on it will add it into your model builder. Alright, now the things that needs to be changed in this physics are, the first thing is the wall condition. I click on this wall option here. I'll change the freeze to be bounce, because it's better to work with bounce wall condition for fairly small particles or cells, which in our case is true. The next thing that we should do is to dictate the particle properties for COMSOL. Now we have 3 different particle properties. The first one is the red blood cells, the second one is the white blood cell, and the last one is circulating tumor cells, or CTCs. So I will change the density of the particles. All of them needs to be 1050 or so kilograms per cubic meter, and the density and the diameter of the red blood cells will be somewhere around like 6 perhaps, and I call that RBC for red blood cell. Right-clicking on the particle tracing for fluid flow, I'll add in another particle properties, call that white blood cell or WBC, and change the density and the diameter. The diameter of red blood cells, of white blood cells, are somewhere around 10 micrometers. Now, the last one will be the CTCs or circulating tumor cells. So we'll add in particle properties, right-click on it to rename it CTC, change the density as well as the particle diameter. Now, as you can see, as you know, CTCs have different diameters based on which cancer a patient is suffering from, but the almost average number would be 20 in diameter. So I'll just type in 20 micrometers for the diameter of the circulating tumor cells. Don't forget to change the units if they aren't already set to micrometers. Now, once we have all the red blood cell, white blood cell, and circulating tumor cell particle properties, now we can add in an inlet for the particles. So I'll right-click on the particle tracing for fluid flow physics and add in an inlet. I'll zoom in. This Adder inlet is the inlet that the paper uses to release the particles. So I'll just click on that face. And up here in the options, we have to change a couple of things. I want one CTC released and 2 red blood cells and 2 white blood cells. I'll first add in the release of a circulating tumor cell. So I'll just have it to be a projected plane grid or random. You can choose whatever option you want. And for the number, I'll type 1. The release time is set to 0. The initial velocity should be the velocity that we calculated in the stationary study. So this should be remained to be expression, and this user-defined velocity should be changed to velocity field. And for the released particle properties, I want the CTCs to be released first. Of course, you can add in as many particles as you want, but for the sake of calculation time, we want it to be as small as possible. So I'll release 1 particle for CTC. I'll right-click on the inlet and duplicate it. I'm going to change the release time for the red blood cells to be 0.01. I can actually leave it off to be 0 as well, but for the demonstration, I want it to be a little bit later than CTCs for red blood cells to be released. The number of particles would be 2, and everything is the same. The velocity field, because we duplicated the inlet, is the same as the first one, and this time the released particle properties should be the red blood cells. And I'll do the same thing for white blood cells. 2 particle releases at 0.02, projected plane grid, the velocity field that we calculated, and the white blood cells. Once we have all the 3 inlets, we have to dictate the forces that act on particles. Now, as you know, one force is the Dean drag force, which I said will be embedded in the velocity field, and we shouldn't add it as a separate force. The 2 forces that we should add separately are the drag forces and the Wall-induced lift forces. So I'll just right-click on this particle tracing for fluid flow physics, and under forces, I'll locate drag and click on it. Once I do, I have to tell COMSOL where in the domain this drag force is exerted on the particles. Now, in the whole domain, the drag force is acting on them. I just click on the whole domain, and once I do, the whole domain is selected and turned into blue, and I can continue giving it other options. Now, none of these should be changed except for this velocity here. That should be changed to the velocity field that we calculated. As you can see, I leave the drag law to be Stokes because we're looking in a pretty low regime of Reynolds. So the dynamic viscosity should be this one here, and I'll click the include wall correlations tick as well. Now the drag force is added to the domain. The next force would be the wall-induced lift force. Now I have to add 2 different vol-induced lift forces, one for the up and down walls, and the other for the left and right, or the inner and outer walls. So I will right-click on the particle tracing for fluid, and under forces, I go and choose lift force. Here in the lift force, we'll first need to give it the domain, which is the whole geometry. I'll click on the geometry and it's selected. And in the lift force, in the lift law option, I click on it. Its default lift law is Safman. We are not looking for Safman here because Safman is pretty low compared to the other forces acting on particles. So we will easily cancel that out and choose vol-induced lift force. Once I click on the vol-induced, these two parallel boundary options appear that I have to tell COMSOL what boundaries are parallel. So I'll first choose the up and down walls. I'll activate the parallel boundary 1 and go ahead and choose the upper faces. Once all the upper faces are selected, I deactivate the parallel boundary 1 and activate parallel boundary 2 to activate the lower faces. Once it's completed, I deactivate this parallel boundary as well and minimize them. The next thing that needs to be changed here is the velocity, which will be changed to velocity field, and the dynamic viscosity. Now I can duplicate this lift force to account for the lift forces from the inner and outer walls. The only thing that needs to be changed is the parallel boundary 1 and 2. I open parallel boundary 1, I clear the selections, I'll do the exact same thing for parallel boundary 2. Activating parallel boundary 1, I'll choose all the outer faces of the spiral. This face, and a quick note that if you are choosing these outer faces, it's a good option to choose this face as well. So I choose this face in the outer faces because it's outer face of this inner inlet. I'll make sure that I choose every single outer face that I have in the geometry. And once I do, I'll deactivate parallel boundary 1 and activate parallel boundary 2 and choose all the inner faces. And now it's finished. I can deactivate parallel boundary 1 and all the remaining options like the velocity field and the dynamic viscosity is duplicated from the lift force number 1. I'll just rename them so we can see better. I'll rename this lift force number 1 to be vol-induced up and down walls. The next one would be vol-induced side walls. And this one is obviously the drag force. One last thing that we need to assign is the outlet. So I right click on this physics and choose outlet. And here is where my particles will go out from the geometry. So I'll, oops, I made a mistake. I'll just click on this boundary here and this one in the outlet of the geometry to have an outlet of particles, and the vol condition is set to freeze so that I can see where my particles are at the end of the spiral. So I've added the particle properties, the vol condition, the inlets for the particles, the drag force, the vol-induced lift forces, and the other two forces that are embedded in the velocity field are the shear gradient lift force and the Dean drag force. I can easily add in a study here This time a time-dependent study because particle tracing for fluid flow needs to be studied as a time-dependent study. So there are a couple of options here that I should change. I want the time to be almost 2 seconds. I believe that should take the particles 2 seconds to enter from here and exit out from the outlets. And I can change the time intervals, and the lower the number I enter here would be the more time intervals that it can see for particles to behave. And I leave the tolerance to be the physics control tolerance. Under the physics and variable selection, I will deselect the laminar flow. I want just the particle tracing for fluid flow to be calculated, and one more important thing is that under values of dependent variables, I will locate values of variables not solved for, and instead of physics controlled, I change it to user controlled, and the method would be solution, and the study would be the study number 1, the stationary study that we calculated the velocity field in. So I select that. Now everything is set up. I'll just right click on study number 2 and call that particle red blood cell, white blood cell, and circulating tumor cells. I'll hit OK and hit compute. Now, it should take a couple of minutes to a couple of hours, depending on your CPU, for this study to be calculated completely. Once it's done, we'll come back and see the actual results that we get. Alright, after a couple of hours, the calculation is now finished. We can see now how the results match with the results taken from the paper. Let's take a look at the paper first to see how we want the particles to behave in the spiral. Now, this first picture here is the inner inlet of the actual inlet of the spiral. You can see that from the outer inlet we have all red blood cells, white blood cells, and circulating tumor cells. Once they are in the geometry, the Dean drag force is acting on them, so they will move towards the inner wall, and once they reach the inner wall, the circulating tumor cells will remain there because there will be an equilibrium between the lift forces and the Dean drag force. But the red blood cells and white blood cells will not have the effect of the lift force because A over DH is less than 0.07 for them, which is the actual threshold for the lift force to be exerted on a particle. So they will move along the Dean drag field to go to the outer wall again, but the circulating tumor cells will remain in the inner wall and they will be captured in the outlet. As you can see, the isolated CTCs will be captured in the inner outlet. Let's see how COMSOL gives us the exact same results. In the simulation, we can see that, well, before I start demonstrating, I want you to know that this red line here is the circulating tumor cell, the cyan line is the white blood cell, and this blue line is the red blood cell. They entered all from the outer inlet, and they started to go from the outer wall to the inner wall. As you can see, they all migrated toward the inner wall, and after a couple of rounds you can see easily that the red line, which is the circulating tumor cells, is still stuck in the inner wall, but those other particles, which are the red and white blood cells, are starting to migrate towards the outer wall. As you can see, while we continue going to the outlets, this red line, which is the circulating tumor cell, is collected in the inner outlets, and these other particles, which are the red and white blood cells, are collected completely in the outer wall. And it doesn't matter how many particles we enter into the particle tracing for fluid flow physics, the result will be the exact same thing. As you can see, this is the isolated circulating tumor cell, and these are the red and white blood cells. And that was the end of the tutorial series on the isolation of circulating tumor cells using a spiral, microchannel, and inertial forces. Take care.